Hello, we're live again. Thank you for joining us on another episode of our DGX Spark live streams. Appreciate all of you for joining us. As always, today we have something special for you. We have a very interesting use case for DGX Spark. We're going to go a little bit into a demonstration of how Michael here at NVIDIA is using it for his telescope rig and to see as far as the stars. So hence the name of this episode is Observing the Universe. So Michael, I'll let you take it away.
Hey, my name is Michael Clive. I'm a senior manager here at NVIDIA, where I run a developer technologies group supporting a lot of our enterprise platform tools like Omniverse, Isaac Robotics, and our cloud stacks like NVCF. Um, my hobby, one of my interests, is space and astronomy. I'm a space industry refugee, who's now kind of working here in AI. But like when I was growing up, I always used to love, planetarium shows. I used to love going with my dad, the Air and Space Museum in DC near where I grew up. And, as, I sort of like, you know, as I, kind of got older, I like, lost a lot of interest and I focused more on the engineering side. I worked in, building rockets and stuff like that. And about, 4 years ago, 3.5 years ago, when my daughter was born, we took her out to, Yosemite, and I'd not been in really clear, dark skies for a long time. And it was my first exposure to like being able to see the Milky Way in my adult life. And I just fell into the hole of astrophotography, astronomy, all that stuff. And it's been a wild ride, a lot of fun. And one thing that is fun about astronomy is that sort of it's as complicated or as simple as you want it to be. You can have an amazing evening out there in a dark sky site with just your eyes or a pair of binoculars, or you can build, the most sophisticated telescope in the world and make amazing discoveries, and anything in between. So Zach, where should I go first?
I think just go straight into your demo.
Okay, cool. So what I have here is I have this DGX Spark sitting here, and what I've created is a AI voice agent to control my telescope rig in my backyard. And so what I'm going to show you is you're going to see a video feed live from my backyard, which I'm going to bring up right now. Grab that. So this is a live video feed from my backyard. You can see my telescope rig sitting there. It's in a park configuration. And actually, let me make that a little bit smaller for you guys. That's better. There you go. And now I'm going to talk to my telescope. So here we go. Hello.
Hello, I am Spark, your telescope-controlled assistant, on duty here in Castro Valley, California at the 140, 980 scope. I'll tell you exactly what you can see through this instrument tonight. How may I help you?
Do you mind pointing the telescope to the planet Venus?
Fluing to Venus. It will be at a low altitude of about 15 degrees, just west of the Milky Way, near the bright star Regulus. You will observe its bright, steady point of light through the 140 aperture. When you have the scope centered, let me know if you'd like to use a filter or start an exposure.
Actually, tell you what. Tell me what satellites are up right now.
Satellites currently above the horizon: TIRSAT, NORAD 58,989 Kuiper 80, NORAD 64,827, Starlink 32,086.
Hey,
You're at 59.
let's track that Cooper 80 satellite. What do you know about the Cooper satellites? Hey, buddy, what do you know about the Kuiper satellites? Bummer. Okay, well, we had the demo curse. So we're just going to end that right there. But typically, what would happen is that the telescope would, the AI agent would tell you about by the Kuiper satellites, and then I could ask it to park the scope, and the scope would be parked. So I kind of ran into some kind of error there that possibly. Oh, I think it came from the actual tablet going off. That's funny. That actually wasn't it was a front end that died. Anyway, so yeah, I guess you want me to go into how that all worked.
Yeah, that was for me, being kind of a fan of photography. That is very cool to see. We have some images that that you took that I'd like to share on
Sure.
screen right now. Some of the audience might want to see it. So I'm going to take the two of us off.
So there's a beauty shot of the telescope with the Spark on it, positioned prominently and beautifully. So what you're actually looking at here, this is a dual telescope rig. I have it set up so there's one telescope that is permanently set up as an astrophotography system, and one telescope that's permanently set up as a visual telescope. That way you don't have to switch between the two. A lot of this system is set up around the fact that I have, young, I have a young family, and I need to, like, stuff needs to go pretty fast. So if I want to show my kids a star, I don't have that much time to show it to them before, it's bedtime or something like that. So I can't really fumble and set stuff up. And you also want to take advantage of any clear night you get for astrophotography. So that's how you end up with a setup like this. The lower telescope, you're going to see some photos off of it. It's a fairly fast telescope. Fast is a optics nomenclature about sort of the focal ratio, and it has an APS-C camera on the back of it. So not a full frame camera, somewhere between full frame and like smaller. That big kind of thing that says QHY on it, that's a filter wheel. And so the way you do astrophotography, a lot of the times you do what's called narrowband imaging. And in narrowband imaging, you basically have filters that notch out individual wavelengths of light that are associated with specific emission lines of material in the cosmos, be it hydrogen alpha or oxygen or sulfur. And then you can compose beautiful images out of those emissions using what's called the Hubble palette or other palettes, and you can get really pretty space photos. And this is all sitting on a mount from this company, 10 Micron from Italy. And what's special about the mount is the mount has very accurate encoders. And the encoders tell the telescope mount exactly which way it's pointing, no matter what. And the mount has a very sophisticated set of algorithms that computes everything from the atmospheric pressure for refraction of the atmosphere to the exact GPS coordinate to the exact GPS time to the actual current shape of the Earth's position and precession in its orbit to correctly lock on to identify targets. So I'm going to pause here if there's any questions.
Yeah, we have a question actually here that says, let me bring that up. What's the name of the AI agent?
I just called it Spark. That's all. I'm not a very creative namer for that. Um, yeah, but actually, if I were, I've actually been thinking about this. I actually possibly, if I continue on this project to the next level, I'm going to reach out to a gentleman named Paul Fellows, who's a distinguished astronomer and kind of a member of the Royal Society, in the UK. And Paul Fellows has one of the best YouTube channels for astronomy related knowledge you've ever found. And I was going to actually request like from him, like, would you allow me to take the transcripts of your lectures and fine tune this model with them so it could contain some of your wisdom? And then, of course, I can offer that model back out as an open weight LoRa patch to GPT 20 billion. Kind of like take, because he is so amazing. So I call it then Paul, if I were to do that, but I haven't done that yet. So now it's just Spark.
I actually have a
So
question.
go ahead.
So, what was the, no pun intended, spark that ignited the idea for you to do this? Was it your kids? You're
So
just staring out in the night sky all night, or what was it?
this is going to get super inside baseball for astronomy people. But basically, if you're using a telescope, you have to want to know what you want to point it at, right? And but each time you want to point at something different, you have to look down at something else. Either have to look down at your phone or a laptop or the hand controller for the telescope. And you have to boop in, like, I want to go to Aldebaran, or I want to go to M42, or I want to. And the thing about astronomy, visual astronomy specifically, not astrophotography, is that everything has to do with the state of your eye. And the eye adapts to the night, adapts to dark in several phases and several modes. One of them is, of course, a pupillary factor, as the pupil expands during the night. And the other one is actually something that occurs in the retina itself. And so what happens is if you're going out there and you want to look at a bunch of stuff, you have to constantly be like moving your head down into a phone and back up to look at the telescope and down into a phone. And even though a lot of the phone apps these days, like SkySafari, have a red light filter that can reduce that, it's still always a losing battle. And so what I wanted to do is I wanted something in which I did not ever have to. I could still have the same experience of working with an advanced, astronomy planning application like a SkySafari or a Stellarium, but without the drag of having to use a laptop. And so I thought, well, it's now gotten to the point where I can run my own voice agent, and let me try running it. And I did, and it works well enough. Especially the really cool thing is I'm very interested in satellite astronomy, and because I've worked on satellite systems, I've worked on space vehicles, and I have a lot of friends still in that business. So like when their space station launches, I'm going to want to be able to track it. And the way that you have to set up satellite tracking is usually a very intense process of picking an orbit and assigning it, and it's a bunch of stuff. I just have a microservice that does all of that now. So I can go up to the thing and say, "Hey, is a space station coming up?" And it'll tell me, and it can aim. And so it's kind of like a time-saving thing that saves my night vision, and also it saves time outside. So I can go outside and like use a telescope quickly before bed, and without having to like strap in for a long evening observing session.
Nice little story.
Yeah.
We have another question here. What are some challenges you had getting the Spark to work for this use case?
So, this was my first time working with ARM architecture. I've not had to build software with ARM before. And there are a couple little glitches here and there as I was taking this from my dev environment, which is an x86 platform, to Spark, in which like things like I'd be running the Kokoro speech. I'm using Kokoro text to speech, and that had a dependency on Triton, and there was not a wheel available for the combination of CUDA, pip, and combination of CUDA, Python, and architecture that I had available in the Triton wheel, distribution server. So I had to, build my own, Triton from source, which, was like, this took time. Then the other thing is that like the Spark's performance is lower than some of the Blackwell GPUs that I might have access to on other systems that I have access to, like a Blackwell Pro or whatnot. So moving down from a GPT 120 billion to GPT 20 billion for performance reasons was another thing that we had to do. I had to do, and then I had to do like a bunch of just like what other arch problems I had. There's stuff that just kind of didn't work because of weird glitches in open source software that was actually not Spark's fault. Like one of the speeches container that I use for voice speech to text, that their repo had a major glitch in it that basically made it fail anytime I tried to add a new model to it. But that's not really Spark's fault, right? That just was that thing, but it's something I had to overcome anyway. I had to actually go to like Docker exec IT, go into a container, and like you said, to like edit out little bits and pieces of code that was causing the error. It was actually quite irritating, but persevered. Yeah, so primarily like Arch and like, the fact that performance is not, the same as a $10,000 GPU.
Great. I'm here just sharing some of the images that you took. I don't know if the audience is interested, but I think, it gives you a good idea of what the end result is.
So I can talk a bit about this. So the Spark voice agent I use for visual astronomy. The goal is to be able to walk out to the telescope array and say, hey, I want to look at a satellite. Hey, I want to look at the double star. And it just does without having me look down. What you're seeing here is some of my astrophotography of various nebula and galaxy inside and outside the Milky Way. And this one is called the Wizard Nebula, and this is a narrowband image. And in this case, what you kind of see, the blue is oxygen, the red is hydrogen. There's a little bit deeper red, which is some sulfur. I was kind of asked by some folks about like kind of how AI is actually impacting astronomy itself, not just this agent that I built, but this image uses some very subtle AI techniques. So in astrophotography right now, there's a little bit of there's some tension between using AI tools versus not using AI tools. And where we kind of landed as a community is that a certain subset of AI tools are valid for astrophotography, and others are, like kind of more general, like the ones that give you stuff that you didn't actually capture are kind of like not seen as like a great contributor to the hobby. But there is this guy, Russell Croman, who's made 3 plugins for the PixInsight software that are GPU accelerated. They run on CUDA, and they're called Blur Exterminator, Noise Exterminator, and Star Exterminator. And what Blur Exterminator is, it is a very sophisticated sharpening algorithm that ensures that the AI convolution that it's doing only ever enhances data you give it. It does not create new data. Noise Exterminator, a little bit on the edge there. If you crank Noise Exterminator too much, it can create detail that doesn't exist. But Blur Exterminator is mathematically composed such that its sharpening kernel only gathers light that you kind of like, created, you captured of your telescope. And then Star Exterminator is kind of just a processing technique where typically what you do in astrophotography is you do if you go to one of the nebulas, so this is a galaxy. So that's the Andromeda Galaxy. So can you go to one of the other ones? I'll tell you when to stop. There you go. So this is the Elephant Trunk Nebula, and the process and this is in the Milky Way. This is kind of high in the night sky right now. If you're in the Bay Area, you can't really see it. This is about 36 gigabytes of data. This is about like 6 full nights of exposure across 6 different filters. So I have like all of the different, narrow bands, plus I have RGB for stars. So what I do is in your process, you take the stars away, and then you process the nebulas, and then you process the stars, and then you reintegrate the image. And that way you can have a much more natural looking image that looks better. And so, there are AI tools for star extraction, and then you can very easily add those stars back in, where they should be.
I think there's some questions that are coming in. If you want to take a second, we can answer one of them. I can read this one out loud. Curious about NVIDIA's telescope AI, when zooming in into an image, how does the AI handle magnification? Is it purely digital, crop based?
This question is conceiving of the thing that's not a well like what I was just saying is that we like in the image you're seeing uh there there is no super resolution. This is just raw pixels with a lot of processing, but not no super resolution techniques, no false detail added, nothing. And that's what I was saying earlier is that this is very much a kind of like a artistic decision in the astrophotography community of not using AI to generate data that you did not yourself capture.
Great. And I think there's another question here. It's asking about the camera feed. I'm taking this question is asking, did it get the camera feed, then pipe it through GPT and then calculate the angles to adjust
That's
the
actually a great question about how the whole thing works, because it's actually a microservice application. There's a lot going on behind the scenes that was not obvious if you did not like because I didn't tell you guys. And the way this works is, I kind of mentioned that the mount itself is quite intelligent. It's the mount will always know how to point to an exact position on the sky, provided you tell the mount exactly what position in the sky to point to. So there's a bunch of microservices in the background that GPT feeds kind of a common name into. Like I asked for the Orion Nebula, right? So it uses a tool call and using an MCP like thing, and it goes to a microservice which takes M42 and it actually figures out, oh, M42 is Orion Nebula, which is actually this object, and then it actually looks up the position in the sky that would be, and then it does what's called a coordinate transformation from J2000 epoch to the today epoch JNOW, in order to make sure that like it takes into account the proper motion and the position of the Earth in its orbit, blah 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 blah, and then it gives that position to the telescope aiming microservice, which then provides that direction to the mount, and then the mount does a motion to that thing. Same thing with planets. If you say, "Hey, I want to go to Venus," it calls a tool. GPT calls a cool tool, and that tool then goes to that a different microservice, which calculates based on the ephemerides of of Venus, where Venus is exactly, and then it tells them out go exactly here. Um, and then enables tracking, and the telescope handles all the tracking over a long period.
There's another question here asking about a mobile use case. Does it run offline?
Yeah, I mean, look, so this entire system runs, on a Spark locally. And in theory, if I take this to a star party, I mean, it'll be a pain in the butt to move that mount, but I have a smaller mount over there that isn't quite as sophisticated as this one, but it's just a back end change. And the Spark is fairly low power. So if you kind of bring like a Jackery box or a power, thing, a power bank, you can take it, you can put your Spark down, bring your tablet, set up a Wi-Fi network, and then yeah, I could bring this out to Yosemite if I chose to.
Great. We have just a few minutes left. I know all of you have some questions eager to ask. Mike has some limited time, so I think maybe we'll take one last question. This might have been repeated, but for those maybe just joining recently, what are some of the challenges for this use case in getting the Spark to work?
Okay, so I'd rather not focus on the Spark. I'd rather focus on sort of like the agent problem, right? Because I could have like a Blackwell NVL72, 40 like I could have a multi-million-dollar computer and still have problems. And the problems are primarily along the lines of AI hallucination when it comes to areas of knowledge in which it has a little bit but not a lot. For example, it'll say something like, Venus is, a waxing crescent phase right now. It doesn't know that. It just made that up. It's made that up because that's what it hears in like Star Talk or other kind of things in this training corpus, right? So there's a desire that I have to kind of create a fine-tuning data set in which I use like actual astrometric calculations to build a gigantic training data set, like 600,000 or 100 or a million lines of things like, on April 21st, 2035, the moon is at a 3/4 phase, those sorts of things, and kind of like burn that into the AI is one idea. Another idea is kind of to heavily prompt the model that anytime it tries to make any judgment about what an astronomical object looks like or where it is in the sky, it has to make a call to a tool that will tell it an actual answer based on an astrometric solution. That's another way to do it. But that's very computationally expensive in terms of the number of tokens, right? It has to do a lot of reasoning in order to do that, call the tool, and then come back. The tool call is very quick because these astrometric solutions can be calculated like blazingly fast, right? The stuff that guys are doing by hand in the 1848. And now I have like, a 20 core, machine to do it. So, like that's one area. Like reducing latency is another area that I really want to improve, and kind of like tweaking its voice activity detection because it's a little bit sensitive right now, and like you can interrupt it by making a loud noise or by coughing, which is this. I think it's the parameter I got to tune.
Great. We're just about out of time. I just want to thank everyone for coming and joining us today. I know it's a bit short, but more incentive to join us on our next live stream, where we'll have more information about Spark, to fill you in on. Thank you, Michael, for coming on. There are a few, I think, assets we would like to share for people. If you want to come and join us on Discord, go ahead and do that. Ask your questions there to Michael or anyone else on our team. We also have our community team email you can use to contact us.
Yeah, it was a real pleasure. Thank you for letting me share. And I'm really happy I was able to, share this project with the wider world. The Spark is a great product. I love working on it. It really makes me happy to get stuff running on it. It's small, it's quiet, it's efficient, it sips power. I couldn't the alternative to Spark on this would be a massive, 1,000-watt workstation. And I have this little thing that can do all of that. It runs 5 models. It's running 5 inference payloads right now. And it's handling it like a champ.
Handles like a champ in a small form factor.
All right.
All right. Thank you guys for joining us. We'll see you next week. Thank you, Michael.